Okay, let's look at motion in a little bit more detail now. Resisted motion, because the reality is, whenever there's motion, there is resistance to that motion. But resistance is always in the opposite direction to the motion. So always in the negative direction, if you define where you're travelling in as positive. That's basically Newton's third law, what we looked at there. So every action equal opposite reaction. So let's look at, basically there's three possible cases we could have. We could have a horizontal line. We're just travelling in a horizontal line. So there's Bob. I'm imagining I'm travelling to the right. So if I'm travelling to the right, that's going to be my resultant force. I always like to define my resultant force to be the direction I'm travelling in. But the actual forces, I've only got one, and that is that resistance, whatever it happens to be. It might be friction, it could be something like that. But gravity doesn't come into play in this one, because gravity, of course, is a vertical force. So I'd simply say, well, all my forces will add up to give my resultant force V minus R, whatever R turned out to be. I'd divide both sides by the mass, and I'd have an acceleration formula that I could then go and work with. So that's if it was horizontal. If it was upwards motion, so now I'm travelling up. So because I'm travelling up, I'll define up to be positive. I'll also have the force due to gravity this time, as well as resistance. So I've got mg acting down, but resistance is also acting down, because it's in the opposite direction to which I'm moving. All my forces must add up to be the resultant force, but they're in the opposite direction, so they're negative. So I'd come up with an equation, minus mg minus r, divide by the mass, and again I'd have an acceleration equation that I could go and work with. Just because there's resistance, it doesn't change basic ideas. The greatest height is still going to happen when velocity equals 0. I mean, it's got to stop and then come down. So okay, the third possible case. If we're moving down, so now I will define the positive direction to be going down. Gravity, well, that doesn't change, that's still going down, but now resistance will be going up. So this time I'd end up with an equation like this. mg would now be positive, because it's in the same direction in which I'm travelling. The resistance will still be negative. Divide through by mass, and there's the acceleration equation that we go and work with. But really, the basic straight line cases, it's going to come down to one of those three. Because if it did come up as at an angle, like say projectile motion, then I would break it up into horizontal and vertical motion. So really, all motion we can consider as either horizontal or vertical. And in the vertical case, we've got two cases. We might be going up or we might be going down. Now with downward motion, we have something called terminal velocity. Terminal velocity is when the acceleration is equal to 0, basically. It's the limiting velocity is another way of thinking about it. As time approaches infinity, what does the velocity approach? So let's look at a question. We're going to do one where we're going vertically up. Initial velocity of u meters per second in a resisting medium, assuming that the retardation due to this resistance is equal to kv squared. And you usually find that resistance is some sort of proportion of velocity or velocity squared. Find the expressions for the greatest height and the time it takes to reach that height. So all these questions start with drawing a force diagram first. So there we are, we're going up. I'm going to define my resultant force, therefore to be going up. So I'm going to draw all the forces. We have the force due to gravity, which is mg, but we also have this resistance. Now, because they've called it retardation, you notice I haven't multiplied by mass. So basically, when it's retardation, it's already a force, so I don't multiply it by mass. In reality, it doesn't really matter, because it's a constant times velocity squared anyway. So whether that mass is in the constant or it's not in the constant, we'll see as we go along. Okay, initial conditions. I know when x equals 0, v equals u. There's my force equation. Resultant force equals all the forces added together. There's two forces we've got there, and they're both in the negative direction. Divide through by mass. Acceleration It's in terms of velocity, this one. So I'm definitely going to use the v to v dx formula, so I can get the v in there. I've made a little one fraction because it just makes life a lot easier, because I'm going to have to turn things upside down, things like that. So turn it upside down, and I now have mv. Oh, I've also divided by the v, you'll notice. And I'm minus mg minus kv squared. So let's separate our variables out. They told me that the initial velocity was u. Initial displacement was 0. So it's 0 and u. We want to know the greatest height. Well, the greatest height is going to occur when the velocity is 0. And I want to find out what x is at that point. That'll tell me the greatest height. What I've then done, notice I played around with this a little bit. I've got rid of the negative by swapping the limits round. I mean, you can always multiply by -1, but swap the limits so you don't have the negative there. The other thing I've done is I've had a look at it and I've noticed, look, I've got v on the top, kv squared on the bottom. I want to create derivative on function. It's going to be a log when I integrate, basically. So the derivative of kv squared is 2kv. So I've created the derivative on top. Well, that means I have to divide by 2k to balance it out. So that's where the 2k out the front has come from. But now I can integrate. So it'll be the log of mg plus kv squared. Substituting u, substituting 0. This step here with the minus, you don't really need it. You could just jump straight to there. Because again, we're talking about logs. So if we know we're going to end up with a minus. So substituting top, substituting bottom. And then I don't know why I turned it into a mixed numeral, but I did. So it became 1 plus ku squared on mg. So there's our greatest height. All right, it also said, work out the time it takes to get to that greatest height. So back to the acceleration equation. But this time, I'm going to use dv to t. And that'll link velocity and time together. And I know it will happen when velocity equals 0. That'll allow me to find the time it takes. So dv to t, yes, I'm going to have to turn upside down again. Separate the variables. And this time, there's no v on the top like the last one. So I don't have a log function. This time, I've got an inverse tan function. Well, if it's inverse tan, I prefer it just to be v squared rather than kv squared. So if you think of your standard integral for inverse tan, a squared plus x squared. Well, that means I'm basically taking the k out of the integral, but then the mg must become mg divided by k. Once again, I've multiplied by -1 and swapped the limits round. Okay. Inverse tan, so it's 1 over a. Well, a squared is mg on k. So 1 over a is the square root of k on mg. Inverse tan, and then again we get the square root of k on mg, that times v. Substitute in u, substitute in 0. Inverse tan of 0 is 0. And so there's the time it takes. Root m on kg, inverse tan, the square root of k on mg, u. That's how long it takes to reach the greatest height. So the key is draw your force diagram. From your force diagram, you'll come up with an acceleration expression, and everything starts from there. From there you can decide, okay, what format do I want acceleration in? Which one am I going to use? Will I use v to t? Will I use d dx of half v squared? Will I use v to v dx? This time I'm dropping an object, 5 kilograms, from a height, and gravitational acceleration is g. We're going to assume air resistance is proportional to speed v, that constant of proportion being 1/8. Find the velocity after time t. Okay, so this time I'm going down, so there's good old Bob. So I'm going to define the resultant force Instead of writing it as mx double dot, I've written it as 5x, but they told me the mass was 5. Force due to gravity, again, instead of writing mg, I've written it as 5g. Resistance, they've told me, is 1/8 of the velocity, the constant of proportion being 1/8. Set up my equation. Divide everything by 5, and I get g minus 1/40th of v. So we want to link velocity and time together, so d to t would be the logical thing to use for acceleration. Again, writing it all as one fraction makes it easier to separate the variables. There we go. I pulled the 40 out the front of the integral sign. Initial conditions for this one, well, if I'm just dropping it from a height, then at time 0, displacement is 0 because I haven't dropped it yet, and velocity is 0 because I'm just going to let it go. So integrating that one, again, we've got a log function. So minus 40 log 40g minus v, substituting in, and we get our 40 log 40g on 40g minus v. But, whoops, let me just go back. That, of course, is t in terms of v. The implication there really is v in terms of t. What's the velocity after time t? So let's now make v the subject. So I've divided both sides by 40, exponentialized. Next thing I've done is turn both sides upside down because I want to make v the subject, so it's handier if v is on the top of the fraction there. It means my index there changes to be negative t on 40. Multiply by the 40g, rearrange the terms, make v the subject, and there we have a lovely expression for velocity. So what is the terminal velocity? Remember I said terminal velocity is acceleration equals 0. So I could go back to the acceleration formula and just say, well, when's that equal to 0? So v equals 40g. But now I've got another way as well. Because I have a velocity time equation, remember I said the other thing that terminal velocity is, as t approaches infinity, what's velocity doing? So, or I could have said, what's the limit as t approaches infinity of the velocity? We've got an exponential curve. It's a negative exponential. So if you were to draw that, it will come down asymptotic to the axis. So as we're approaching infinity, the e to the negative something will approach 0. So again, I'm just left with 40g. So there's two ways you can work out terminal velocity. You could use acceleration, or you could use the velocity time equation. All right, we're now going to find an expression for displacement in terms of time. Well, velocity is dx dt, so I'll use that. Again, separate my variables. When time was equal to 0, displacement was equal to 0. So let's integrate. Substitute in t, substitute in 0. Be careful, remember, it's so tempting to say substitute in 0, we get 0. But when we're dealing with an exponential, of course, e to the power of 0 is 1. So I get the negative 40 there. And, well, I expanded the whole thing out and got that expression for displacement in terms of time. Okay. So our Cambridge 4A and 4B, plus a handful out of Patel as well.